Welcome back. This will be a second video lecture on section 4.2 from the text. The topic is determinants. In our first video lecture, we covered determinants of n by n matrices and the geometry of determinants. We'll pick up in this lecture with properties of determinants, determinants of elementary matrices, and finally determinants and matrix operations. So let's begin with properties of determinants. Let's begin with theorem 4.3, which gives us a catalog of important properties of determinants. Now, throughout this theorem, we're going to be seeing matrices A, B, and C. Those are all square matrices. Now, property A says that if capital A has a zero row or a zero column, then the determinant of A is equal to 0. Property B says that if the matrix capital B is obtained by interchanging two rows, or for that matter, two columns of capital A, then the determinant of B is equal to the negative of the determinant of A. Property C says that if A has two identical rows or columns, then the determinant of A must be equal to 0. Property D says that if capital B is obtained by multiplying a row or column of A by K, then the determinant of B is going to be K times the determinant of A. Property E says that if A, B, and C are identical, except that the ith row or column of C is the sum of the ith rows or columns of A and B, then the determinant of C is simply the sum of the determinants of A and B. And finally, property F says that if B is obtained by adding a multiple of one row or column of A to another row or column of A, then the determinant of B is equal to the determinant of A. Now, from among these 6 properties, the 3 that I want to highlight as the most important are properties B, D, and F, because these pertain to simple row operations. So property B here is talking about a type 1 operation. If we perform a type 1 operation on the matrix A, that's going to flip the sign of the determinant. Property D is referring to a type 2 operation. If B is obtained by multiplying a row or a column of A by K, then the determinant of B is K times the determinant of A. So that's the effect of a type 2 operation. And then finally, property F, if B is obtained by adding a multiple of one row or column of A to another row or column, then the determinant of B is equal to the determinant of A. And so that's showing us the effect of a type 3 operation. So what I want to do is go to the document camera and explore some of these properties here outlined in theorem 4.3. So join me at the document camera for that. All right, welcome to the document camera. We're going to look at the proof of theorem 4.3. In particular, I want to pay special attention to parts B, D, and F, because these correspond to a type 1, a type 2, and a type 3 operation on a matrix. So let's spend our time concentrating on B, D, and F. And I also want to concentrate on just the 2 by 2 case. I think we'll see all we need to see. We'll learn everything we need to learn just by looking at the 2 by 2 case. The other cases can be obtained from the 2 by 2 case by induction. So what I want to concentrate on in all of these cases is a 2 by 2 matrix A with, let's say, entries A, B, C, and D. We know that the determinant of A is simply AD minus BC. Now let's take a look at the proof of B. In this part B, capital B is a matrix obtained by interchanging two rows of the matrix A. We want to show that the determinant of B is equal to the negative of the determinant of A. So in part B, our matrix capital B has to be what I get by interchanging these two rows. And so row 1 is going to be CD and row 2 is going to be AB. And when I look at the determinant of B, we get CB minus AD. Now by factoring out a -1, this is equivalent to the negative of AD minus BC and that's clearly the negative of the determinant of A. And so that verifies property B, at least in the 2 by 2 case. All right, let's take a look at property C. In property C, the matrix capital B is obtained by multiplying a row of the matrix A by some scalar k. And we have to show that the determinant of B is k times the determinant of A. So let's take a look at a matrix B in this case. So we're looking at property D. Let's say our matrix B is obtained by multiplying, let's say, row 2 by the scalar k. So we'll have, for our entries, AB and k times C and k times D. That's our matrix B. We've altered the matrix A by multiplying row 2 by k. Now the determinant of B is going to be A times KD minus KC times B. Now in this case I can factor out a common k, and I'll have AD minus BC multiplied by k, but AD minus BC is the determinant of A, so this is k times the determinant of A, and we're done. And that's how we prove property D. Finally, let's look at property F. In F, B is obtained by adding a multiple of one row to another row, and then showing that the determinant of B is just the determinant of A. Okay, so let's imagine that we form B by taking lambda times row 1 and tacking that onto row 2. So our row 1 will be unchanged. But in row 2, we're going to see C plus lambda A. And in row 2, we'll see D plus lambda B. So we've taken a multiple lambda of row 1 and added it onto row 2. Now let's compute the determinant of B. That's going to be A times D plus lambda B minus C plus lambda A times B. We can distribute. And after we distribute, we see that there's this common term here. There's a lambda AB and a minus lambda AB. They cancel each other out, and so we're just left with AD minus BC, and that's just the determinant of A. So in the case of a type 3 operation, we can see that the determinant of B is unchanged. It's equal to the determinant of A. Now, that proves properties B, D, and F. Some of these other properties are actually quite easy to show if we understand B, D, and F, and some basic things about the Laplace expansion theorem. So if we want to take a look at property A here, it says if A has a 0 row or a 0 column, then the determinant of A is equal to 0. Now that's very clear just by imagine doing Laplace expansion along that row of zeros or that column of zeros. So that's relatively easy to show. If A has 2 identical rows or 2 identical columns, then the determinant of A is equal to 0. Well, let's just imagine that row 1 and row 2 are identical. Then we can do one of these type 3 operations, and we can use one row to eliminate the other row. The determinant would have to be unchanged according to property F, but there would also now be a row of zeros, and now we could use property A to show that the determinant of the matrix that's left must be equal to 0, and therefore the determinant that we started with must have been equal to 0 as well. So the heart of theorem 4.3, and this is really what we're going to need going forward, are properties B, D, and F pertaining to the type 1, type 2, and type 3 operations that we would typically apply to a matrix to effect reduction to, let's say, a reduced row echelon form or even a row echelon form. Okay, let's head back to the class notes and continue. Let's recast parts of Theorem 4.3 into the language of row operations. Now, in each one of our examples, a matrix A is being transformed into a matrix B through a single elementary row operation, and we want to detect how the determinant of B is related to the determinant of A. In our first example, we perform a single type 1 operation. So the matrix A is transformed into the matrix B by simply exchanging rows I and J. Now what theorem 4.3 tells us is that the determinant of B is therefore the negative of the determinant of A. In our second example, we're looking at a single type 2 operation. The matrix A is being transformed into the matrix B by multiplying row I by a scalar lambda. And what the theorem tells us is that the determinant of B is simply going to be lambda times the determinant of A. And finally, let's look at a single type 3 operation. The matrix A is being transformed into the matrix B by multiplying row J by lambda and adding that onto row I. And what the theorem tells us is that whenever we perform a type 3 operation like this, the determinant of B will in fact be equal to the determinant of A. A single type 3 operation does not change the determinant. The determinant of B will equal the determinant of A. Now these observations have some computational and theoretical consequences. Let's look at a computational consequence first. Find the determinant of the matrix A, this 3 by 3 matrix that we see here. Now, reduce A to a triangular matrix through elementary row operations and use theorem 4.3. So here's what I did. I took the matrix A and using 5 elementary row operations, I was able to reduce it down to a matrix I'm calling A star. Now we can think of A star as a row echelon form of the matrix A, but more importantly, I want to think of A star as an upper triangular matrix. Now, here's the specific recipe that I used. In step 1, I took -1/2 times row 1. That's a type 1 operation. In step 2, I did a type 3 operation. I took 1 times row 1 and added it onto row 2. In step 3, I took a -2 times row 1 and added it onto row 3. In step 4, I did another type 1 operation. I took 1/3 of row 2. And finally, in step 5, I did another type 3 operation, 2 times row 1, added onto row 3. Now, what theorem 4.3 tells us is that the determinant of A star is linked to the determinant of A through these row operations. In other words, by keeping track of these row operations and the effects that they produce, we can now calculate the determinant of A star in terms of the determinant of A. Now, in this particular case, only these type 1 operations make any kind of contributions or changes to the determinant. We know that this one will have the effect of multiplying by -1/2, and this will have the effect of multiplying by 1/3. These type 3 operations don't alter the determinant. So, according to theorem 4.3, the determinant of A star is 1/3 times -1/2 times the determinant of A. That's the link between the determinant of A star and the determinant of A. Now, in this case, we actually know how to compute the determinant of A star, and that's the whole point of this method. We should rather think of this as a way of calculating the determinant of A. Why is the determinant of A star easy? Because it's upper triangular. So when we get to an upper triangular matrix, the determinant is simply the product of its diagonal entries. And so what this allows us to conclude is that the determinant of A is going to be a -2 times 3 times the product of the diagonal entries of A star, 1, 1, and -2. In other words, the determinant of A is simply 12. So here's what we can take away from this example. Imagine that we were given a large matrix. Let's say the matrix A was a 10 by 10 matrix. Now we would have 2 different ways of computing the determinant. Now method 1 would be to use the method of cofactor expansion, the Laplace expansion theorem. But I think we would see that we would quickly be waiting in calculations. In the first step, we'd replace the 10 by 10 matrix with a sequence of 9 by 9 determinants to calculate. And each of those 9 by 9 determinants would be replaced by a sequence of 8 by 8 determinants to calculate. And that process would go down until we would have a very, very, very lengthy sequence of 2 by 2 determinants to calculate. And then we'd have to riffle it all back together to get the determinant of the original matrix A. On the other hand, it's conceivable that we could take that 10 by 10 matrix and simply do a sequence of row operations to reduce it down to its row echelon form, get it into an upper triangular form, and compute the determinant using the determinant of the upper triangular matrix that would be simply the product of its diagonal entries and the multipliers that we would get from the row operations themselves. So we could imitate the procedure that we used in this problem. Computationally, that would be much cheaper and much easier. So that's a computational takeaway. We can calculate determinants now by row operations. All right, now let's get into some of the theoretical consequences of Theorem 4.3. Now let's look at a first theoretical consequence of Theorem 4.3. And this is an extension of a theorem that we already know for 2x2 matrices. So if A is a 2x2 matrix, we know that A is invertible if and only if its determinant is not equal to 0. Now it turns out that that is just true in general. So let's imagine we have a square matrix A, and we go through a sequence of elementary row operations to reduce A down to a matrix A star, which is its reduced row echelon form. So A star is the reduced row echelon form of A. Now what Theorem 4.3 tells us is that the determinant of A star can be connected to the determinant of A through these elementary row operations. In particular, we want to keep track of the type 1 and type 2 operations that have occurred along the way. Now what this tells us is that there's going to be a non-zero multiplier, let's call it mu, that allows us to conclude that the determinant of A star is simply that multiplier times the determinant of A. And again, this multiplier is just encoding the type 1 and type 2 operations that have been used along the way. Now, that also allows us to write the determinant of A in terms of the determinant of A star. So the determinant of A is 1 over mu times the determinant of A star. Now, let's follow this chain of implications. The determinant of A is not equal to 0 if and only if the determinant of A star is not equal to 0. And that follows immediately through these two relationships, right? These determinants will be equal to 0 or not equal to 0 simultaneously. Now, let's look at this second implication. If the determinant of A star is not equal to 0, that's completely equivalent to A star being equal to the identity matrix. If A star is anything other than the identity matrix, it's going to have a row of zeros in it, and that row of zeros will produce a determinant that's equal to 0. So these two statements are absolutely equivalent to each other. Finally, if A star is equal to the identity, that's completely equivalent to A being invertible, and that follows from our fundamental theorem on invertible matrices. So if we step back and look at this, A is invertible is completely equivalent to the determinant of A not equaling 0. And that's an important theoretical development. And let's enshrine that in Theorem 4.6. A square matrix A is invertible if and only if the determinant of A is not equal to 0. Now back in section 4.1, we saw how useful this result was to help us find the eigenvalues of a 2x2 matrix. What Theorem 4.6 is going to allow us to do is calculate eigenvalues for square matrices in general. One of our next big theoretical results about the determinant is that the determinant of a product of matrices is the product of the determinants. And in order to understand how that comes about, we're going to have to delve into the determinants of elementary matrices. Now let's first study what Theorem 4.3 tells us about the determinants of elementary matrices. And all we have to do is remember that an elementary matrix is the result of applying a single row operation to the identity matrix. Let's take a look at this first case. Let's imagine we take an identity matrix and we switch two rows. We switch row I and row J. That's going to produce an elementary matrix. And we know that when we do a type 1 operation, the determinant of E is going to be the negative of the determinant of the identity matrix, which is 1. So the determinant of E is going to be -1 in this case. Let's look at a type 2 operation. In a type 2 operation, we're just multiplying a row by some scalar, lambda. So let's take the identity matrix and let's multiply row I by lambda to produce the elementary matrix E. What Theorem 4.3 tells us is that the determinant of E is going to be lambda times the determinant of the identity matrix, which is 1. So the determinant of E is simply going to be lambda. Finally, let's apply a type 3 operation to the identity matrix. Let's take the identity matrix, let's multiply row j by lambda and add it onto row I. That's going to produce an elementary matrix E. And again, what theorem 4.3 tells us is that the determinant of E in this case will be 1 times the determinant of I, which is equal to 1. So the determinant of such an elementary matrix will equal 1. So we can easily determine the determinants of elementary matrices corresponding to type 1, type 2, and type 3 operations. And this is enshrined in theorem 4.4. So let E be an n by n elementary matrix. If E results from interchanging two rows of the identity matrix, then the determinant of E is equal to -1. If E results from multiplying one row of I by k, then the determinant of E is equal to k. And finally, if E results from adding a multiple of one row of I to another row, then the determinant of E is equal to 1. Now let's study an important consequence of theorem 4.4. So let B be an n by n matrix, and let's suppose I transform B into a matrix B star by a single type 2 operation. So I'm going to take row I of B multiplied by lambda and transform B into B star. Now let's take an identity matrix of exactly the same size, and let's perform exactly the same row operation. So I'm going to take row I of the identity matrix multiplied by lambda and produce the elementary matrix E. Now we know that when I take the matrix E and multiply by B on the left, that's going to have the same effect as performing that row operation. So in other words, B star is just the product of E and B. Now let's see what this means about the determinants. The determinant of E times B is simply the determinant of B star because of the equivalence or the equality between these matrices. So the determinant of E times B is the determinant of B star. On the other hand, theorem 4.3 says because B star came about from the matrix B by this type 2 operation, we know that the determinant of B star is just lambda times the determinant of B. On the other hand, our previous result says that lambda is the determinant of E, and so I can say that lambda times the determinant of B is the determinant of E times the determinant of B. Now, if we step back and look at this, what this is telling us is that the determinant of the product E times B is the product of their determinants. Now, I showed this to you for a type 2 operation, but exactly the same result would hold if we did a type 1 operation or a type 3 operation. So in general, when we look at a single elementary matrix multiplying B, we're going to know that the determinant of their product is the product of their determinants. So in other words, it doesn't matter if that elementary matrix comes about from a type 1, a type 2, or a type 3 operation. Now let's enshrine this in lemma 4.5. Let B be an n by n matrix, and let E be an n by n elementary matrix, and it doesn't matter if that comes about from a type 1, a type 2, or a type 3 operation. Then the determinant of the product of E and B is the product of their determinants. And this is a provisional form of a deeper theorem that we're approaching. Now we can easily extend lemma 4.5 recursively. So for example, let B be an n by n matrix, and let E1 and E2 be n by n elementary matrices. Then by doing two successive applications of lemma 4.5, we would know that the determinant of E2 times E1 times B is the product of the determinants, determinant of E2 times the determinant of E1 times the determinant of B. Now let's use some of the things we've discovered about determinants of elementary matrices to allow us to unlock some interesting connections between determinants and matrix operations. And let's begin with theorem 4.7. Now if A is an n by n matrix, the determinant of k times A is simply k to the n times the determinant of A. In other words, if we scale the matrix A by a factor of k, then its determinant will be the determinant of A scaled by a factor of k to the n. Now, I claim that if k is equal to 0, there's nothing interesting here to say, because on this side, k times A will simply be the determinant of the 0 matrix, which is 0. And on the right-hand side here, k to the n will be equal to 0. And so when k is equal to 0, this is just saying that 0 equals 0. On the other hand, when k is not equal to 0, then I claim we can build up this matrix k times A through a sequence of elementary row operations. So let's think about it this way. Let's think about how we can write the matrix k times A as a sequence of n elementary row operations. In step 1, E1 is just going to simply affect the change of multiplying row 1 by k. And now E2 will be multiplying row 2 by k. And this process will continue until I get to the matrix En, which will simply multiply row n by k. So I can think of k times A as the effect of a sequence of n elementary row operations. Each elementary row operation is multiplying the successive row by a multiple of k. Now, what does lemma 4.5 and its extensions tell us? It says the determinant of k times A is simply going to be the product of these determinants. But each of these determinants is going to have a value of k. So I'll have k to the n times the determinant of A, which is precisely what theorem 4.7 is telling us will happen. So this is how we can get at theorem 4.7 through looking at it through the lens of elementary matrices and row operations. Our next big result is theorem 4.8. If A and B are n by n matrices, then the determinant of the product of A and B is the product of the determinants. Now, the proof of this is not difficult, but it is a little bit more involved. So let's go to the document camera and look at the proof of theorem 4.8. All right, welcome to the document camera. Let's look at the proof of theorem 4.8. Now, before we prove the theorem 4.8, I just want to mention a result that we'll need along the way. And this is just a result about matrix inverses. We could have proved this back in chapter 3. It says this. It says that the matrix product A times B is invertible if and only if A is invertible and B is invertible. All right, so let's establish this fact first. Now, one direction we already know. We know that if A and B are both invertible, then their product is invertible. And in fact, we know what the inverse is. It's going to be B inverse times A inverse. That's something we did establish back in chapter 3. Now let's get this direction. We want to show that if A times B is invertible, that means that both of the underlying square matrices are themselves invertible. Now, let's see how that proof would go, right? So let's assume that A times B is invertible. What does that mean? It means there's a matrix X that multiplies A times B on the right to produce the identity, and it also multiplies A times B on the left to produce the identity. Now, by association, I can rewrite this product as A times BX equals the identity. And by association, I can write this as XA times B is equal to the identity. But we now know that if there's a matrix that multiplies A on the right to produce the identity, that is sufficient to show that A is invertible. So this product is showing me that A is invertible. And now we know that I have a matrix X times A. There's a matrix that multiplies B on the left to the identity matrix, and we now know that that is sufficient to show that B is invertible. Okay? So, knowing that A times B is invertible, proves that both of the underlying parts, both A and B, must be invertible. Now, with that result in mind, let's go to the proof of theorem 4.8. And we have to break the proof of theorem 4.8 down into two basic cases. All right, so we're going to look at the proof of theorem 4.8, part 1. Let's assume that A times B is not invertible. Okay? Now, if A times B is not invertible, then one of the two underlying matrices, either A or B, is also not invertible. Okay, now let's look to see why our result about the determinant of the product equaling the product of the determinants must be true in this case. So if I look at the determinant of AB, that has to equal 0 because AB is not an invertible matrix. And if I look at the product of the determinant of A times the determinant of B, one of these two must be equal to 0 because either A is not invertible or B is not invertible, possibly both. But we know that one of these two is not invertible, so one of these is equal to 0. And so this product is also going to equal 0. And therefore, the determinant of AB is equal to the determinant of A times the determinant of B vacuously because they're both equal to 0. So there's really nothing very interesting going on in this case. If AB is not invertible, then one of these two is not invertible, and we just have this 0 equals 0 case. All right, the more interesting case is the case where A times B is invertible. Now in that case, we know from our little lemma above here, if A times B is invertible, that implies that A is invertible and B is invertible. Now we'll only make use of this first one. This was the one we'll make most use of. Now we know that if A is invertible, from our fundamental theorem of invertible matrices, we know that the invertibility of A means that A can be expressed as a product of elementary matrices. So we know that we can write A as a product of some elementary matrices. Let's say K of them. And now by applying our lemma 4.5 recursively, we know that we can write the determinant of A as the product of these, as a product of the determinants of these elementary matrices. Okay, so that's a fact that we'll need. And now finally, let's look at the product A times B. A times B can be rendered as E1, E2, down to EK times B. We're simply rewriting A as a product of these elementary matrices. And now we can use our lemma 4.5 in this context and know that the determinant of A times B is equal to the determinant of E1 times E2 up to EK times B. But by lemma 4.5, again, replied recursively, we can one by one peel the determinants of these elementary matrices off until we have determinant of E1 times the determinant of E2 on down to the determinant of EK times the determinant of B. But now we can stare at this and realize that this product of these determinants of these elementary matrices is simply the determinant of A. And that establishes our result. So in the case where A times B is not invertible, we have this kind of vacuous equality 0 equals 0. And in the case where A times B is invertible, we can use our theorems We have theorems about invertible matrices being expressible as the product of elementary matrices, and we have our lemma 4.5 that tells us how we can write the determinant of A times B as a product of determinants of elementary matrices times the determinant of B, and we get our result through applications of those theorems and lemmas. Okay, so that gives us the proof of this all-important theorem 4.8. Let's go back to the class notes and explore some consequences of this theorem. Our next theorem, theorem 4.9, is particularly pleasing. It says, if A is invertible, then the determinant of the inverse of A is equal to the reciprocal of the determinant of A. Now, another way of writing this is to say that the determinant of A times the determinant of A inverse is equal to 1. Now, let's see why this is an actually relatively simple consequence of theorem 4.8. We know that A times A inverse is equal to the identity matrix, and that means that the determinant of A times the determinant of A inverse must equal the determinant of the identity matrix. But the determinant of the identity matrix is equal to 1, and therefore this result, theorem 4.9, as pleasing as it is really a simple consequence of theorem 4.8. Our next and last theorem of the section is theorem 4.10, and it says this: for any square matrix A, the determinant of A is equal to the determinant of A transpose. Now, this result actually follows quite easily from the relationship between A and its transpose and the Laplace expansion formula. So, the Laplace expansion formula for the determinant of A along its first column is equal to the Laplace expansion formula for A along its first row. So we can easily see the relationship between these two determinants by looking at the Laplace expansion formula for A transpose along its first column and for the matrix A along its first row. Now that brings a close to this section 4.2. And so I will see you again for our next lecture, a video lecture on section 4.3. Until then, take care. Bye-bye.